Hello, I'm Yaren.
Hi, this is Tohu.
Hi, I'm Kriti Shukla.
I'm Sarah Willen, and welcome to our presentation on the identification and modification of instruments' tonal signatures.
So something that we've noticed is that even when two instruments are playing the exact same note, the human ear is able to tell the difference between them. So for example, a trumpet playing at a certain frequency doesn't sound the same as a violin. During lab 2, we noticed that there were differences between the FFTs of different instruments, even when they were playing the exact same note. So we decided to explore the relationship between the differing FFTs and the way qualitative sound is perceived by the human ear. Our major question or motivation is essentially what makes instruments sound different from each other. So basically, to visualize the sounds produced by different instruments, it's important to use and understand Fourier transforms. Fourier transforms take audio files from the spatial domain, put them through the above equation, and then use Euler's identity to break the audio down into sine and cosine components. These components can then be visualized as a frequency versus amplitude graph. Unfortunately, Fourier transforms can be really computationally expensive, so often they're approximated using discrete Fourier transforms, which take the above equation and turn it into a summation over discrete points instead of a continuous integral. The FFTs we use in this experiment are an example of discrete Fourier transforms. Another thing that's important to understand about audio is that different types of instruments propagate through the air differently. In this experiment, we focused on two classes of instruments, string and brass. The sound created by string instruments depends heavily on intrinsic properties of the string and the medium it is in. So, for example, the mass density of the string or the density of the air. Meanwhile, the sound created by brass instruments depends heavily on the pressure in the valves of the instrument as well as the material of the instrument and the shape of the valves, which changes depending on the way a person blows into it or pushes certain buttons. So overall, due to the differences in how sound intensity works for the two types of instruments, we hypothesize that string instruments will tend to have similar FFT signatures that will be different from the FFT signatures of brass instruments. We also predict that brass instruments will produce more overtones in their FFTs since their material and shape produces a greater amount of high amplitude overtones. Finally, because we know that Fourier transforms are able to effectively model sound as frequency versus amplitude graphs, we predict that simply adjusting these graphs will heavily influence how instruments sound, and making the graph of one instrument look like the other will also make the sound of one instrument sound like the other.
In collecting our data, we tuned each of our instruments to record a note D4 at 293 Hz, saving the audio as WAV files. We collected recordings for the violin and viola, as well as the piano, guitar, ukulele, and trumpet. After collecting our data, we ran the WAV files through a template Jupyter notebook that we created. After reading the file and trimming the data to exclude extraneous noise, we performed a Fourier transform on two datasets at a time. As you can see in the Fourier transform here, many overtones are present in addition to the original 293 Hz. Using the second segment of code shown, we adjusted the peaks of one Fourier transform to look like another, for example violin to guitar. We used a range of plus minus 140 Hz for scaling down to minimize noise, and a range of plus minus 5 Hz to scale up for the same reason. Once the Fourier transform looked qualitatively close enough to our desired signature, we used the last segment of code shown to perform an inverse Fourier transform and write our data to a WAV file.
Briefly, I'll go over our experimental procedure. First, we all tuned our instruments using the same online tuning app to ensure consistency in the note we produce. Then we recorded ourselves playing the sound. We uploaded the recording to Python as a WAV file for computational analysis. First, we applied an FFT on the WAV file to identify the fundamental frequency and overtones. This is the instrument's tonal signature. We observed the shape of this graph and noticed the relationship between the amplitudes of each overtone compared to its following overtone. Next, we uploaded another instrument's WAV file and extracted the tonal signatures. By qualitatively observing the relationship between overtone amplitude to one another, we modified each individual overtone of the to-be-mutated instrument's tonal signature. Once the tonal signatures matched relatively well, we applied an inverse FFT and wrote the data as a WAV file to listen.
Procedure shown in the video to conduct 5 trials with mutations. The first trial we have here is making the plucked viola sound like a ukulele. The first and second plus here are the original FFTs of the plucked viola and the ukulele respectively. Both of them have very few overtones, and the intensity of the overtone diminished very quickly. The third plot here is the result after we scaled the viola FFTs and made it look like that of the ukulele. So now let's listen and please try to remember their sound. the viola sound totally different after mutation, right? And it does sound like ukulele as we expected. Then we try to convert a bold viola to the trumpet. So when we compare the FFTs, surprisingly, we noticed that the bold one has more overtones than the plucked viola. However, just like we anticipated, the trumpet has more overtones, extending to about 4,000 hertz. But beyond our expectation, the first overtone of the trumpet has a much larger intensity than the fundamental frequency. Now let's listen, and probably you should turn down the volume a little bit. Maybe it's not that obvious, but the sound of the viola changed and had some features or quality of the trumpet. Since we only have a limited amount of time, I'm not going to talk too much about the rest of the trials in detail, but if you're interested, feel free to go to our files and listen after class. But notice that the bolt string instrument here, the bolt violin, has more overtones than the plucked guitar. And again, the bolt violin has more overtones than the piano. This is the ukulele to piano trial.
As we hypothesized on the basis of material and structure, the trumpet showed far more high-amplitude, high-frequency overtones than the string instruments, extending almost to 4,000 Hz. Interestingly enough, the first overtone of the trumpet had an amplitude 10 times higher than the fundamental G4. We did not, however, predict that the bowed recordings of the violin and viola would have more overtones than the other string instruments. In processing our data, we found the mutation of the data to be much more convincing between string instruments compared with the mutation between strings and brass. And when mutating between bowed and plucked instruments, such as violin to guitar, the result is less convincing than the mutation between two staccato recordings, such as ukulele to piano. This suggests that the overtone signature is not enough to fully reproduce the notes of different instruments, and that there are more considerations to be made.
In review, the objective of our project was to 1. Identify the tonal signatures of different instruments playing the same note, and 2. Modify the relative amplitudes of overtones in relation to each other to match a different instrument's tonal signature. Using the principle of Fourier transforms, we were able to break down audio into sinusoidal components. These graphs identified the tonal signatures of different instruments. After adjusting the overtones relative to each other, we were able to produce a synthetically modified sound wave that resembled a different instrument. As we saw in the discussion, the brass instrument had considerably more overtones than string instruments, and string instruments resembled each other closely. We also found that, although tonal signatures matched quite closely, there were still noticeable differences in sound quality due to tone quality, the medium it's being played in, and if the note was being played with vibrato or not. In the future, another experiment could be to see how many overtones are actually significant to the instrument before it starts sounding like a different instrument. We could repeat the same process as our experiment and remove potentially insignificant overtones one by one. Another aspect to consider is the shape of the note. For example, we noticed that the plucked versus bowed playing of the same instrument produced different shape of the note. Another iteration of this project could be creating a program for automated overtone changes through quantitative overtone comparison. In order to do so, the program would compare the ratio of one overtone's amplitude to another and apply that same ratio to the instrument that is to be mutated. Then we could redo this process for a multitude of notes and potentially turn an entire song into another instrument. Another idea is to understand what makes tones more pleasing. For example, what makes a Stradivarius violin better than a standard one? Can we see this reflected in the tonal signature? With our beginning experiment, we've unlocked the potential to create even new instruments that no one's ever heard of. Using Fourier transforms and some physics, we discovered the tonal signatures of instruments to quantitatively understand why instruments sound different.
Thank you for listening to our presentation.